Okay, today we're going to talk about rotational kinetic energy. So rotational kinetic energy of an object is given by the sum of all the little half mv squareds of the distributed mass. Okay? So we have to take into account the fact that the mass is distributed. When we were looking at linear motion, we were looking at just the translation of the center of mass. Now when we go to rotational motion, we have to take into account that the object is spread out. So this sigma here means the sum of the kinetic energies of all the little pieces of mass all spread out around the thing compared to the axis. Okay? If we substitute in the rotational quantities for each of these, because you know that there's a relationship between V and omega, and between M and R and I, we come up with this. Right? Looks very similar. Because this is the rotational inertia, right? The moment of inertia. This is the angular velocity. Corresponds very well with the one that we already have seen before. So, an object that has both translational and rotational motion also has both translational and rotational kinetic energy. There is, in fact, kinetic energy within the rotation. And the way we write it is 1/2 the mass of the object times its velocity of the center of mass, plus 1/2 the moment of inertia times the angular velocity around the center of mass. So, when using conservation of energy, we have to take into account both rotational and translational. We look at these objects. They all have the same potential energy up here, but the time it takes to get to the bottom is different. So, here's a hoop, here's an empty can, a solid cylinder, a sphere, or a box. Sliding. The box sliding on a frictionless surface gets to the bottom quicker. There's no rotational inertia holding it back. Let's have a look at an example. What will be the speed of a solid sphere of mass m and radius r when it reaches the bottom of an incline if it starts from rest at a vertical height h and rolls without slipping? Here we're into one of these problems where we're not actually going to use numbers. Ignore losses due to dissipative forces and compare your result to that for an object sliding down a frictionless surface. That would be an object of exactly the same mass. So, we use the law of conservation of energy, and we must now include rotational kinetic energy. The total energy at any point, a vertical distance y above the base of the incline, is going to be given by this. Total mechanical energy is going to be the kinetic energy, translational, plus the rotational kinetic energy, plus the gravitational potential energy. So now we can equate the energy at the top of the incline, where the height is h, with, and v and omega are both 0, to the total energy at the bottom, where y equals 0. So we've got, since we know that the total mechanical energy must be conserved, we can compare this. This is the top now. These two terms become 0. This is mgh. These two terms remain. That term goes to 0. So we now look to the table and text to find the expression for the moment of inertia for a sphere about an axis through its center of mass. All right, so we have the moment of inertia for the center of mass of the sphere as 2/5 mr squared. Since the sphere is not slipping, the velocity of the center of mass is equal to the speed on the edge relative to the center. Do you remember that bicycle wheel where we were looking at the velocity of the hub of the bicycle wheel and then said, let's have a look at it from the point of view of someone on the bicycle? And so now the velocity of the part touching the road was equal but in the opposite direction. Remember that? Okay. So we can put the angular velocity equal to the velocity divided by the radius. So what we end up with now, substituting in, is 1/2 m, the velocity of the center of mass squared, plus 1/2, we change for the moment of inertia that we've looked up, and instead of omega we put v over r, all squared, and it becomes equal to mgh. The interesting thing is, you can see now that a lot of stuff is going to cancel. There it is again. The m's and r's all cancel, and what we're left with is 1/2 plus 1/5 v squared equals gh. It still doesn't matter. It still doesn't matter what the masses are, and it still doesn't matter what the radii are, which is fortunate, because when we were doing things before with translational motion, it didn't matter either, they cancelled. So we come up with a velocity for rolling by converting that rolling motion and translational motion, the square root of 10 over 7 gh. So that's what our velocity for the sphere would be. The velocity of an object sliding down the same incline with a frictionless surface is 1/2 mv squared equals mgh. There is no rotational component. Again, the m's cancel, and what we're left with is the velocity for sliding is the square root of 2gh, which is larger than this velocity for rolling. As stated there. So it takes longer, or it takes a bowling ball longer to get down a slope than it takes, say, something on a very frictionless, icy slope to go down. Because we have to build up a rolling motion if it's non-slipping. Torque also does work as it moves the wheel through an angle theta. We have an angle theta, it's moved it through a distance L, so the work is equal to the force times that angle, that path length delta L. That's the same as what we were doing before. We said the force multiplied by the displacement in the same direction. And if we make this small enough, then this displacement is in fact in the same direction as the force. So we can now write that that's Fr delta theta. And since the torque is equal to Rf, what we find is that work now can be expressed as tau delta theta, or the torque times the change in angle. Gives you the amount of work done.